In this presentation, we will implement 1-bit full adder using multiplexer. The mux that I am using is 4x1 mux, and the first thing that we require is the truth table. And I hope you are already familiar with the full adder. And in this, we are having three inputs A, B, in which A and B are the two numbers, 1-bit numbers that I want to add, and C in is the carry from the previous sum. S is your sum, the output of the addition, and CO is the carry output. If there is any carry, then this CO will reflect it. So it's a very simple thing. We already know this, and we also know that how these values, the output S is being evaluated, and also the C out is being calculated. So the next thing that I have told you in the previous presentation is to see the number of variables. So in this, I'm having three variables A, B, C in, and depending upon three variables, I will make a 8-cell K map. So this is our 8-cell K map. There is one difference from the problem that we did in the last presentation, is that in that there was only one output, F, but in this case we are having two outputs, sum and carry output. So what I need is another K map. This K map is, let's say, for sum. This is for sum. Now I want another K map for the carry output. So I will copy this, copy, and then paste, and we are having a 8-cell K map, a separate 8-cell K map for the carry output. Similarly, I will require another mux, 4x1 mux. This 4x1 mux is for the sum, and we need one more 4x1 mux for the carry output. So I will copy this, copy, and then paste. So we are having everything which is required to do the implementation. So let's move. The next step is to fill these cells depending upon the values written here. So we are having 0, then 1, then 1, 0. I'm not writing down the zeros. Okay, then 1, 0, 0, 1. So again, this is a checkboard configuration, you can see, and we will do the groupings later. First, let's fill this map for the carry output. 0, 0, 0, 1, then 0, 1, 1, 1. Fine. So this is how it looks. Now we have to decide for our selector variables. As you know, in 4x1 mux there are two selector variables, S0, S0 and S1. Now I will assume that S0 is your B and S1 is your A. In this particular case, if I have taken BCI as my S0 and S1, then it would be a lot easier for us to evaluate the values. But I don't want to do that. I want you to show every possibility in this particular method. So I have taken B as your S0 and A as your S1. Now we will make a small table for the selector variables that we used to do. So this is your A, this is your B, and then I'm having my output S. I'm doing for this particular K map, and this is for S, so the output will be S. And the four possibilities: 0, 0, 0, 1, 1, 0, 1, 1. Fine. Okay. Now when A is 0 and B is 0, which means when S is 0 and S1 is 0, the output will equal to I0. Similarly, I1, I2, I3. So I have to find out the values of this input, I0 to I3. So for first case, when A is 0 and B is 0, let's see this K map. When A is 0, A is 0 for this complete row, okay, but B is 0 for only the first two cells. Okay, so this is when A is equal to 0 and B is equal to 0. The shaded portion shows the A is equal to 0 and B is equal to 0. And as we are working for the min terms, I am not going to see the zeros, but I will see only 1. Okay, so when it is 1, the value of C, because A and B are the selector variables, so the only thing left is Ci. So the Ci will act as our input. So we have to see only for Ci because A and B are your selector variables. So for this particular cell, the value is 1, and for this cell the value of Ci is 1, which means it is Ci. So our I0 is equal to Ci. Fine. So let's see the next case when A is 0 and B is 1. So A is 0 for this entire row and B is 1 for the last two cells. Fine. So let me shade it down. For these two cells, B is 1, and in this case for the last cell there is 1. Okay, and the value of Ci is 0. You can see the value of Ci is 0, so I will write it as Ci complement. Let's see the third case in which A is 1 and B is 0. A is 1 for this entire row, okay, and B is 0 for the first two columns, this yellow shaded portion. And in this case there is 1 here, and for this cell the value of Ci is 0, so it is Ci complement. I hope it's very simple for you to understand, and we will do the same thing for the last case when A and B both are 1, and it is the case for the last two cells. So I will shade this down, and in this the 1 is here, and for this cell the value of Ci is 1, so it is Ci. So I can say that we have done with our sum, and this is your I0, I1, I2 and I3, and I0 is Ci, so I will write Ci. I0 is Ci, I1 is Ci complement, I2 is Ci complement, and I3 is Ci, and this is your sum S, and these are your selector variables B, A. So this is how we have implemented the sum. Okay, this sum has been implemented by using this 4x1 mux, a single IC. However, if you remember, this sum is equal to what? A XOR B XOR Ci. So we need two XOR gates to implement this sum, but in this case when using the multiplexers we only require a single IC. So this is the advantage that I have been talking since a long time. So let's move to a carry output. We will do the same thing, and I guess I will leave it as a homework for you to determine the value of the carry output and implement it in the 4x1 mux, but I will definitely write down the inputs so that you can check your answer. This is 0, this is your Ci, this is your Ci, and 1, and this is your carry output. The selector variables are again same B, A. So do it yourself, and if you face any problem let me know in the comment box. So see you in the next presentation.